Okay, today we're going to do case 4 from chapter 9. It's on my website. Scroll down until we get to chapter 9, case 4, but the data from case 4 comes from case 1. Case 1 was the sigma known case. Case 4 is the sigma unknown version of that same problem. Remember in case 1 that every time I hit F9 on the keyboard, the observations in column A changed. So each time I hit the F9, I get a new random sample of size 50. So this might be sample 5, sample 6, sample 7, sample 8. So what we're going to do is we're going to copy this data here, and we're going to paste it into case 4. So because the observations are simulated, what I'm going to do is I'm going to right click and then paste special values. Now in case 4, when I hit F9, the numbers in column A do not change. So now I have a given sample of 50 golf balls, and how far they flew once the golf ball was put on a driving machine in some very large field house. Okay? So the first thing we want to do is read the problem, and the problem says use a sample of 50 golf balls from case 1 to see if the company's golf balls fly further than 285 yards. And then alpha, or significance, is 1%. Now, the phrase in red here, that right there is the variable, and since we have a sample of 50, we can think of that as mu, or the population mean. And then, so the red thing is the red phrase is the population mean, and we want to know if it is greater than 295. So 295 is the manufacturer's claim. So the manufacturer's claim is 295 yards. If the manufacturer is claiming that its golf balls go more than 295 yards, so that's a claim. The alternative hypothesis in math terms, as a mathematical statement, is HA, the alternative hypothesis, is the red Greek letter mu is the average flight of the company's golf balls greater than 295, and 295 is the manufacturer's claim. The null hypothesis is the opposite of that statement. The null hypothesis always includes equals, as you can see right there, equals. So the null hypothesis, HO, is the average flight of the company's golf balls fly at most 295 yards. Okay? Now another way to state the alternative hypothesis is in difference form. So all I did here is I took the 295 and I subtracted it from both sides of the inequality. So mu minus 295 is greater than 0 is equivalent to mu greater than 295. They're equivalent. For example, if the Greek gods of numbers say the true mean is 300, so mu is 300, that is greater than 295. Over here we have 300 minus 295, which is 5, and that difference is greater than 0. So we can use either form. I like this form here because the point estimate of this difference is the numerator of the test statistic. In part B, we will determine the critical value of the test. The significance value is given from the problem. Alpha, significance, is 1%. Now, the alternative hypothesis, remember, tells us what kind of test it is. In this case, the alternative hypothesis is saying it's an upper tail test because mu is greater than 295, or the difference in these two values is positive. So that's telling us an upper tail test. Upper tail test and lower tail test, you divide the alpha by 1. So to get the critical value of the test, we go to column 0.01 of the t-table. Now, why are we using the t-table? Because remember, when sigma is known, we use the standard normal table, or what I like to call the z-table. When sigma is unknown, as is the case here, we use the t-table, or t. The degrees of freedom is the value n minus 1. Why is that? Because we don't know the population variance. The sample variance we can compute, and we will later on. We can compute the sample variance to estimate the population variance. The divisor of the sample variance, if you remember, is n minus 1. So the degrees of freedom in a sigma unknown problem is equal to n minus 1. And the sample size here was 50. How do I know it's 50? Well, when we copied in the data, we had copied in 50 observations. And you can see that in the gray box just to the right of the white cursor. So the sample size is 50. With a sample size of 50, the degrees of freedom are 49, and the critical value of the test is found in row 49 and column 0.01. Okay, so let me open up the t-table. That's the standard normal table, or as I like to call it, the z-table. The t-table, we got to be in column 0.05, right? Or 0.01, we're in column 0.01. Column 0.01 here. And row 49. So we're in column 0.01 and row 49. In row 49, column 01, the t-value is 2.405. So I'm going to copy that and paste it right here. Okay. Now, one real quick point here, because the alternative hypothesis is indicating that we have an upper tail test, mu greater than 295, the t-critical value is positive. If the alternative hypothesis said mu less than 295, then we'd have to make the t-critical value negative. But it's positive here because we're talking about an upper tail test. In part C, we want to calculate the test statistic. And I call that t-stat because the test statistic is t distributed due to the fact that the sample size is 50 or more and the population standard deviation is unknown, which is why I have the S here in green. The S is in green because I want to emphasize the fact that we're talking about the sample standard deviation. If we knew the population standard deviation, we'd replace the S with sigma. And this I'd call this a z-stat. But again, remember, this is a sigma unknown problem. So we don't know sigma. We have to estimate sigma with the sample standard deviation. In the numerator of the t-stat, notice that we don't have mu here, the population mean. We have x bar, which is the sample mean. And we have the difference between the sample mean and mu zero. Mu zero is the manufacturer's claim. If I knew the population mean, this would be mu. But we don't know the population mean. That's the whole point of the problem. But we estimate the population mean with the sample mean. So the sample mean is the point estimate of the population mean. And in Excel, we find it by just typing equal average. And then we highlight the data. And our sample mean is 325.126. Now, all of us in class today are going to have different values of the sample mean. Why? Because remember, when we pulled this data from case 1, we all got different numbers. We all have different samples of size 50. So some of you might see 327.3, some of you might see 324.98, yada, yada, yada. So all of us are going to have different sample means because we all have different samples of size 50. So remember, the sample mean is the point estimate of the thing that we cannot know, the population mean, which is why the sample mean and the population mean are all in red. Okay? So the sample mean is the point estimator of the population mean. The point estimator of the difference here, the point estimator of the difference, I'm going to call this diff. The difference between the sample mean and the manufacturer's claim, in my case, is 30.126. Now, what does that mean? Well, we're always going to have a difference. The probability that your sample mean exactly equals the manufacturer's claim is 0. So we're going to have a difference. We might have a negative difference, we might have a positive difference. So there's going to be a difference. But the question here is whether that difference is significant. We want to know if that difference is positive and significant. For an upper tail test, the question is whether the difference, mu minus 295, in this case x bar minus 295, we want to know whether that difference is significant and positive. If this were a lower tailed test, then we'd be interested in whether the difference is negative and significant. If this were a two-tailed test, we want to know if that difference is insignificant. Okay, so we have an upper tail test. We're really interested in whether this difference here, there is a difference, and it's positive. But we're interested in whether that difference is positive and significant. We can't know that until we compute the t-stat and compare it to the critical value. Now, the sample standard deviation is the estimate of the population standard deviation. And we compute it in Excel by typing stdv.s. Remember to put an equal sign in front of it. Highlight the data, and then hit enter. We do .s because sample. If this were .p, we'd be doing the population standard deviation. In other words, if we had p here, we divide by n, 50. If we do .s, we're divided by n minus 1, 49. So you got to remember that. We're doing a sample, so we need to do stdv.s, sample standard deviation. And the sample standard deviation is 12.763. And you guys will notice that if you look at your classmates' spreadsheet and you compare those to mine, we all have different sample standard deviations. Why is that? For the same reason that we all have different sample means. We all have different samples, so we all have different sample means, and we all have different sample standard deviations. Now, the standard error is the thing down here in the denominator of the t-stat. I have it written as square root of the sample standard deviation squared divided by n. So I'm going to write that right here. I'm going to type equal. I got to change the color of the font. Equal square root s squared. So I'm going to square that. And then I'm going to divide by the sample size. So my standard error is 180495. And we all have different standard errors. Why? Because we all have different sample standard deviations. Why do we all have different sample standard deviations? For the same reason we all have different sample means. We all have a different sample of size 50. Now the test statistic, which I call T-stat, the test statistic is the difference divided by the standard error, and it's 16.690. Now because the test statistic is greater than the critical value, we have evidence in support of the hypothesis. In other words, when the test statistic is bigger than their critical value for an upper-tailed test, the difference is positive and significant. So we have evidence in support of the alternative hypothesis here. So we are going to reject the null hypothesis. And you don't just say you reject the null hypothesis, you say you reject the null hypothesis at the significance level. We can reject the null hypothesis at 1% significance. Now, if you tell that to your CEO, your chief production officer, production manager, or whatever, and they don't have very much training in statistics, they're not going to know what you're saying. So what are you saying? Well, when you reject the null hypothesis, you're accepting the alternative. And we can reject the null because the benefit of the doubt is with the null. And we know that because the null always includes the equal sign. So when we reject the null, we're accepting the alternative. So let's go back up to the original problem. And remember, that's the alternative hypothesis in word form. The company's golf balls fly further than 295 yards. So we're going to copy that, and we're going to paste it down here. So we're going to say we can conclude that, and then I'm going to paste the alternative hypothesis. Rejecting the null hypothesis. When we reject the null hypothesis, remember that's saying the alternative hypothesis is true. When we reject the null hypothesis, we can conclude that the company's golf balls fly further than 295 yards. So in the context of this problem, rejecting the null hypothesis at 1% significance is equivalent to saying the company's golf balls fly further than 295 yards. And that's it for case 4.